Welcome to Lesson 8 of Puzzles to Exercise the Mind. In this lesson, we have a number of different and somewhat unrelated puzzles. And the first one is the coin problem, which I'll talk about in the next slide. The coin problem involves making exact change from different values of 2 or 3 or 4 or 5 coins. The examples we're going to look at involve just 2 coins, or should I say coins of 2 different values. So the first question is, what is the largest amount of exact change one cannot make with coins of value 2 and 5 units? Then I'll ask you the same question if you have coins of 3 and 7 units. So there's no limit to the number of coins you have in these 2 questions. And just to give you an example, so for if you have 2 and 5, of course you can't make change for 1, you can't make change for 3, but you can for 4, and of course 5, because you could use 2 of the coins of value 2 for 4 and 1 for 5, and then 6 you could use 3 of the 2. So the question is, what's the largest number where you can't make change? Then the same question for 3 and 7. So think about this. It's pretty easy for 2 and 5. You'll see that you quickly get to a point where you can make change for all future values. 3 and 7 takes a little bit longer to figure out. I have the solution here for the 2 problems. So as I said, the one was 2 and 5 coins, or coins of values 2 and 5. It's pretty easy. You can't make change for 1. Of course, you can make it for 2. For 3, you cannot. And then for 4, you use 2 of the coins of value 2. For 5, then 6, you use 3 of the coins of value 2. And then 7, you just add 2 to 5. And 8, you add 2 to 6. So you'd have 4 of these. And you can, once you get 2 in a row, you can just keep adding 2 to it and get all future values. That's why I stopped here. Now with the 3 and 7, it's the same idea. Once you get 3 in a row, you can just keep adding 3 to those 3 and go on perpetually. So the question is just figuring out what's the largest amount which you can't make exact change for with 3s and 7s. And you get to a solution pretty quickly. 1 and 2 you cannot make exact change, and 3 of course you can. 4 and 5 you can't. But then you can use 2 3s to make change for 6. 7 of course you could use 1 7. Then 8, there's nothing here. There's no combination of 3 and 7. You can make 8. 9 you could use 3 3s. 10 you could use a 3 and a 7. And then 11 you're stuck again. There's nothing, no combination of 3 or 7 to make 11. But then the next 3 work. You could do 4 3s for 12, 2 3s and a 7 for 13, and then 2 7s for 14. And then after that you could just add a 3 to get 15, a 3 to this one to get 16, a 3 to this one to get 17, and you can just keep going. In general, the problem that we've been discussing is known as the Frobenius coin problem, or the Frobenius problem. It's named after mathematician Ferdinand Frobenius. We do have a general solution, however, but before you look at that, or I go to it, you may want to pause and try a more complicated problem like 7 and 11. That'll take you a bit longer to find the pattern. The basic idea is you want to find 7 change amounts in a row that you can make, and then after that you just keep adding 7 to each one, and you can keep getting every possible change amount after that. So here's the general solution. For 2 coin values A and B, where A and B are relatively prime, so they have no common divisor other than 1, the largest number that cannot be represented as a combination of 2 coins of these values A and B is A times B minus A minus B. So for the problem we looked at, 3 times 7, we can check it here. 3 times 7 is 21, minus 3 minus 7, it's 11, and that was the answer we got on the last slide. So checked out for that one example. The formula was discovered by mathematician James Joseph Sylvester in 1882. For 3 or more coins, no closed solution is known. In other words, no solution of an equation like this, but there are algorithms known for finding solutions. And they're discussed further in this Wikipedia article. I'll put the link in the information to this video, so you don't need to copy it down. So we have a completely different type of problem here. It's more geometrical. Determine 2 squares that isolate each dot into a separate region. So the idea is, let's just maybe draw one square to give you an idea of what I'm asking here. So if I drew the square like this, I didn't draw it that nicely, but if I drew 2 squares, let's say this and this, and I know they don't look like squares, but you get the idea. So if I drew these 2 here, then this point would be isolated, this would be isolated, this would be isolated, but these 3 are together in the same problem here. So this is not a valid solution. What you want to do is draw 2 squares. They don't need to touch the boundary. They can be interior. So you want to be able to have each dot in a separate region enclosed by lines like this here and this here. And the lines could be the edge, or it could be the squares. Okay, so I'll give you the answer on the next slide, and you may want to pause here and kind of play around with it a little bit. Well, here's one answer. We have the red square. It's kind of been rotated 90 to 45 degrees, and then we have a smaller green square here that's inside, and you can see that each dot is in a separate region, bounded either by a side of a square or the edge of the larger enclosing square. All right, so I have another problem related to this, almost the same problem. If you're allowed to draw your square outside of the box, or should I say your squares, or outside of the box, there's another solution. You might want to see if you can figure that one out. And if not, I'll show you the solution on the next slide. So here's the out-of-the-box solution. We have these 2 squares are rotated 45 degrees from the original square. And again, you can see where each dot is in a separate region. So here you go. I didn't get either one, so don't feel bad if you didn't figure it out. I'm not great at geometric solutions, but I think it's good. Even if you don't get it, it's kind of good to play around with trying to find a solution and then just studying the solution once you see it. So we have a different problem here. We want to connect the letters, like letters, with lines. They can be curved. You're not allowed to go outside of the box, and you can't cross the lines you draw. So let's do an example here. So if I connect A like that, for example, then I can get B like that, and then we're stuck. C, there's no way of getting C. So without crossing these lines. So you may want to play around with it. It is possible to connect the A to A, B to B, and C to B, C without crisscrossing any of the lines. I'll show you the solution on the next slide. So here's the solution, or one possible solution. The trick is A goes around B and then up over C and then down to A. So that allows for B to go around this way and then C to go directly. And I guess you could go the other way. You could go from A this way above B and then down to A, and then you would connect B directly and you may want to try that. So a little bit hard to see if you need to play around with it a bit, but again, this is one of, I guess, two solutions as far as I could tell. We have another geometric type of puzzle here on this page. What is the total number of ways a regular polygon can be divided into triangles by connecting the vertices with the line segment? The line segments aren't allowed to intersect. So I could have made this convex polygon, but I thought the point it gets across was just regular polygon. So that means the sides are the same length and the interior angles are all the same. So I'll give you an example here. You have a square, and there's only two ways of dividing this into triangles by connecting vertices. One is here, and then there's the symmetric one where you connect going the opposite way. So the answer for four-sided is 2, and the question I'll ask you is to do it for 5-sided, and I'll show you the solution on the next slide. For a 5-sided figure, there's 5 different ways of dividing it into triangles, and I should note here that these, you could rotate this one into that one, but we're kind of distinguishing the sides. You could maybe think of the labels being A, B, C, D, and E. And so the vertices, I should say, and the sides are considered different. So looking at it that way, you can start with this vertex and connect across to these two, and then move to this vertex and do the same thing, and then move to this one, and so forth. So you get 5 different solutions in the case that you have a 5-sided regular polygon. So again, I'll ask you have a look at it for 6. It gets harder as you get into more sides, and there's more possibilities for doing the connectivity. So we'll see what that looks like. And again, you're not allowed to crisscross, so you can't take another line from, say, here to here and get smaller triangles. That's not allowed in this particular problem. For 6-sided figures, which we have here, there's 14, I believe. Let's see, there's 6, and 6 is 12. Yeah, there's 14 solutions. The first set of solutions are across the top. You notice we did the same game as we did with the 5-sided figure. We took a vertex and drew lines across to the other vertices that weren't adjacent. Then we did it here, here. We just kept moving around. So that would give you 6 different ones, but that's not the full set. You can kind of do this zigzag, like I guess an N shape here. And then you can move the N 3 different ways in here. And then you have this is more of a Z shape. You can't equate this one to this one here that's going in different orientation. So you get 3 of these, and then you get this clever one here where you connect this way, and you're left with a triangle in the middle, and there's 2 ways of doing that. So as you can see, the complexity gets harder as you move into a larger number of sides for our polygon. The problem we've been looking at is one of a class of problems whose solutions are governed by something called the Catalan numbers. The Catalan numbers are a sequence of natural numbers named after Eugene Catalan. He lived in the 1800s, though they were previously discovered by a Chinese mathematician, Ming Tu. Sorry for the pronunciation. That was roughly 100 years before. And here's a list of the numbers. This is considered the 0th, so they start counting from 0. This is the first. This is the second Catalan number. Remember, this is our solution for the square, and 5 was our solution for the pentagons, and 14 was our solution for the hexagons, 6-sided, and then 7 8-sided, and so on. And you can see the numbers get big pretty quickly. There's also a formula. It's given here, 2n factorial divided by n plus 1 factorial times n factorial for n equals 0, 1, 2, out to infinity. I did a little example here for our case here. This would be 0, 1, 2, 3, 4. So we put in 4 and we get 2 times 4, then 5 factorial, 4 factorial in the denominator. This is 8 factorial, but the 5 factorial cancels the first 5 and you just get 6, 7, 8 divided by 4 factorial. Then the 2 times the 4 cancels with the 8, 3 goes into 6, 2. And then you just get 2 times 7 or 14. So that checks out with our solution. There's a book, the Enumerative Combinatorics, Volume 2 by Richard Stanley, that has 66 different interpretations. So there are 66 different problems. They don't really look all that the same at face value, and they all have as their solution these Catalan numbers. I'll show you an example on the next slide of another problem that has the same solution. We have another example of a problem that has a solution being the Catalan numbers. And we'll take a look here. We have these 4 by 4 squares, and we want to find the number of roots going from one corner to the other without crossing the main diagonal. Excuse me. And you have to follow along the lattices, the lines here, these straight lines in the grid. So you can see here, this is one way, and then you can go this way up. You can think about going through a city street grid pattern, and how many ways can you get from this point to that point where you can't cross over the middle diagonal, and you can't go diagonally. So here's another solution, here's another solution. So for 4 by 4, n equals 4, we see that we get 14, which is a Catalan number, and in general, if you take the 5 by 5 or 6 by 6, you can just look up, the number of solutions by the checking the Catalan number. So that's another example, and I'll give you one more on the next slide. We have another problem that has the solution being the Catalan numbers. Given a round table with 2n chairs, in other words, an even number of chairs, with one person sitting in each chair, how many ways are there that each person can handshake with somebody else without 2 pairs of hands crossing each other? So for example, if we had 2n equals 6, in other words 6 chairs, then the answer would be 5. In general, the answer is a Catalan number n. If you have 2n chairs, the Catalan number n gives you the number of possible ways of handshaking without crisscrossing. And I have a diagram out on the next slide, which I'll show you. So here's a depiction of the handshake problem with some solutions for n, 1, 2, 3, and 4. So when n equals 1, remember there's 2n chairs and 2n people, so there's only one way for them to shake hands. Then when you have n equals 2 or 4 chairs, 4 people, they can shake hands this way or that way. They can't go this way and that way because then they would be crossing. Then for n equals 3, these are the possible solutions. You can see there's 5. That was the example we gave on the previous slide. And then when n equals 4, in other words, 8 chairs, it was 8 people, you have these various ways of shaking hands without crisscrossing each other, and that's 14. So that's, again, the Catalan number. Okay, so that's just 2 out of many different problems that have the Catalan numbers as a solution. So it's sort of a very popular sequence of numbers that turn out to be solutions for many different problems. I'll give you a few references on the next slide, so you can, if you want to dig into more detail concerning Catalan numbers. I have a few references here for your further study. The Wikipedia article, Catalan numbers. I got some of my information from that I have on the, not the last slide, but the slide before was the lattice and going from one point to the other. Then there's the online encyclopedia of integer sequences, the OEIS, which has a ton of thousands of different sequences, including the Catalan numbers. And you get a lot of additional references there and a lot of information. That goes on for quite a bit. And then there's the book I mentioned earlier, Richard Stanley's Enumerative Combinatorics, Volume 2, second edition from Cambridge University Press, 2023. And it's actually the addendum to this book, which is of interest in terms of Catalan numbers. Unfortunately, the author made this available, or at least right now, it's as of January 25th, 2025. This is a workable link, and I was able to access it. So if you go there, you'll get this addendum, which is quite long, and that has a lot of information on Catalan numbers also. So you may want to check that out. We have the blocks problem. I'm going to give you the simplest version of it, then we'll look at some more complex versions as we proceed. But you have 6 blocks, 2 of each type. 2 with a 1 on it, 2 with a 2, and 2 with a 3. And you want to arrange them in a row like I've shown down here, under the condition that the 1 blocks have 1 space between them. So, for example, you could put a 1 block here and here. The 2 blocks have 2 blocks between them, so you could put a 2 block here and here. And then the 3 blocks have 3 blocks between them, so you could put well, I've covered a space here, but you could put say a 3 block here and one. No, you can't put a 3 block here. You could put a 3 block, say here at the beginning, and you would have 1, 2, 3, and then you would have to put the other 3 block here. So the hard part is figuring out where these fit. And I'll give you a hint. You can't put them in these, either in this space here or this space here, because you would run off either side trying to leave 3 spaces and then put in the 3 block. Okay, so I'll give you the solution on the next slide. It's not, I don't think it's too hard. Just fool around with it and and there's 2, I believe there's 2 solutions. I'll show you one of the 2 solutions. Okay, so here's one solution. 2, 3, 1, 2, 1, 3. Let's check each block type and make sure they're correct. So they have a 1 here, and then there's a space. There's another block, I should say, and then there's a 1. So there's 1 block between the 1s, and then we have a 2 blocks and a 2, and then we have a 3, and we have 3 blocks and then a 3. Okay, so I'll give you another problem which is harder. It'll take a little bit more effort to play around with it, but it's same problem, except now you have 1, 2, and 3 and 4 blocks, 1, 2, 3, and 4 blocks, and you have 2 of each. And for 1, 2, and 3, you have the same rule. And then for the 4 blocks, as you might expect, you have to have 4 spaces between them. So you need to line them up again in a row. And you might want to play around with that. Then I'll give you the one of the solutions on the next slide. So here's one solution, and we'll check it out again. I didn't bother drawing blocks. I just put numbers in a row, but you get the idea. So the 1s are 1 apart. See, the 2 have 2 positions between them. The 3 has 1, 2, 3. That's fine. And the 4 has 1, 2, 3, 4 positions between them. I took this from the Wikipedia articles, giving credit there. It's called Langford pairing. And this was discovered by a mathematician, C. Dudley Langford. He was watching his child play with blocks, and I don't know if it was a boy or girl, but let's say it was a girl. She kind of had the blocks, and it was the 6 block case. We have the 1, 2, and 3, and she had them lined up, and the pattern such that there was 1 space between 1 and 2 between 2, and 3 between 3. And he got thinking about the more general problem, and it turns out there's a whole lot of work that could be done here to solve generalizations of this problem. But let me just read a little bit of what I took out of the Wikipedia article. So these are called Langford pairings, named after Dudley Langford. Also called a Langford sequence, is a permutation of 2 to the n numbers, where you have 2 1s, 2 2s, whatever you want to go up to, 2 n's. We went up to 3 and then 4, in which the 2 1s are 1 unit apart, the 2 2s are 2 unit apart, and the more generally 2 copies of each number k are k units apart. And he first posed this problem in 1958, the year of my birth, actually, although I've only known about this recently. So I'll talk a little bit more about this on the next few slides. There's concerning some of the generalizations where you have, in fact, it turns out, I'll pose this to you. Try it with 5 for 1 1, 2 2, 3 3, 4 4, and 5 5, where the 5s need to be 5 spaces apart. And then I'll explain that problem in the next slide. It turns out, and sorry for doing this to you, but it turns out there's no solution for 5 blocks. There's a number of cases where there's no solution. So hopefully you didn't try for too long, or you realized that there wasn't a solution. So we can prove that. We have 5 blocks. We have 10 positions that we need to put them in, 1 to 10. Right? We have 2 of 1, 2 of 2, all the way up to 5. So I'm going to prove there's no solution here. Let A and A plus 2 be the positions of the A block, so the 1 block, excuse me. So A could be 1, 2, it could be all the way up to 8, and then A plus 2 would be 10 in that case. And then let B be and B plus 3 be the positions of the 2 blocks, and C be the positions of, and C plus 4 be the positions of the 3 blocks, and so forth. So we're basically setting variables for where the 1, 2, 3, 4, and 5 blocks can be, and then we'll work through this to show that it's not possible to find a solution for n equals 5. So if there is a solution, then the following must be true, and this is the key to solving the problem. So that, again, these are variables, A plus 2, but they each one of these, B plus 3, they need to equal one of the numbers in our list from 1 to 10. So if we just add all these together, A plus 2, B plus 3, all the way up to the possible positions for the 5 blocks, then we don't know what the values for A, B, C, D, and E are, but we know that they have to be from the numbers 1 to 10. And so the sum here needs to equal the sum from n equals 1 to 10. I ran out of space, but this is 1 plus 2 plus 3 all the way up to n. So I just used the summation notation. So we know this from our very first lesson. If you recall, we had the formula for the sum of the first n numbers. It's n times n plus 1 over 2. So that's 55. Then on the left, we have 2 A's, 2 B's, 2 C's, all the way up to 2 E's. So we have 2 times the sum from A to E. And then if you just add the 2, 3, 4, 5, and 6, you get 20. And then subtract the 20 from the 55, and you get 35. So you have an odd number here, and 2 times anything is an even number, so you can't have an even number equal an odd number, which means this is impossible. Okay, so, and there's other cases which I'll describe. I won't prove it, but I'll describe the other cases where there's no solution. For a given value n, whether or not there's a Langford pairing possible depends on the remainder when you divide that number by 4. So if you divide the number by 4 and get a remainder of 1 or 2, which I've expressed here as 4k plus 1 or 4k plus 2. That's just the structure of, in other words, if you had 5, it would be 4 times 1 plus 1. It would be in this form here. So if you're in one of these two forms, there's no solution. So we saw for 5, we didn't have a solution. And then if you're in the form 4k, in other words, if you're divisible by 4, so just picking a number 20, we would know that does have a solution. It may not be easy to find, but we know there's a solution. And if it's a remainder of 3, that would also have a solution. So 20 and 23 would, n equals 20 or 23 would have a Langford pairing. An algorithm exists to find a solution in the cases where a solution exists. It's not a simple algorithm, it's fairly complex. And the various algorithms and solutions are described in several places, but this article here gets into a lot of depth. And again, I'll put the link in the description to this video, so you don't need to copy this, but there's actually even some software, some programs that you can run to find solutions for larger values of n where a solution exists. Okay, and I think there's still some open issues. The other thing I should mention is for different values, like n equals 7, for example, there's more than one solution. We saw that even for these simpler ones. And I don't believe that problem has been solved. We don't know in every case how many solutions exist other than going through the algorithms, which can be very time consuming for some of the larger numbers. Okay, here's a simple problem. I saw this on Facebook, actually. Some company was advertising an online music service. It was classical music, and it said $20, 60% off. And I needed to stop for a minute and say, I was just wondering, what was the original price? How do you go about calculating that? So it's not a hard problem, and you could probably do it in a few minutes, but I'll pose it as a problem, and then I'll give you the solution on the same slide. So you may want to pause your video here if you don't want to see the solution, because when I come back, I'm going to just go to the same slide and show you how to do it in general. Okay, I'm back, and so what was the original price? That was the question. So we can write this out, and we can take the words and write it out as an equation. So $20 now, 60% off the original price. So X is the original price, and it's minus 60% of X. So that's what this line is telling us if we convert it to an algebraic equation. And we just subtract the 0.6x from x, and we get 0.4x. And then we divide 0.4 into 20, and we get 50. So it was originally $50. You might even be able to guess that, but if it was a more complicated numbers here, like $23, 69% off, what was the original price? Then you can't do it in your head, and you want to, unless you're really good at it, you want to kind of write it down this way, and then you end up doing a different division here at the end. This question here was one of several questions from the first SAT test. I believe it was 1926. and there was a very short amount of time on average to complete a question, like maybe 20 or 30 seconds. This question here came in a section that had multiple sequence questions. Most of them were easier, so someone may have been able to do those in like 5 to 10 seconds or a little bit less, and then that would have left them, maybe a few minutes to work on this particular one here, which you can see it doesn't just jump off the screen at you. It's not obvious. So that was one thing. And then, of course, in 1926, they didn't have computers or calculators. So I assume the students were much better than we are today in doing quick calculations by hand. So that would have been another advantage they had in terms of solving something like this. Okay, so have a look at it. I mean, try the usual things, see if you can divide one number into the other. If that looks like that might not be too promising, then you can try taking the difference and seeing if there's a pattern there. And clearly there's sort of a down and up pattern here, so that complicates things. And I'll give you the answer in the next lesson. So have a look at it and see if you can figure it out. We have one last problem in this section. I'll give you the answer in the next lesson. Let's look through it here. So Xavier can mow a lawn in 6 hours. Eves can mow the same lawn in 5 hours. And Zachary takes 3 hours to mow that same lawn. If all three work together and don't interfere with each other, how long will it take for the three to mow that same lawn? And assume that these rates are at a particular length of grass, or the lawn has been growing for say 2 weeks, and they can each do it in this amount of time, given that much of growth, and so we have the same growth again, and we're able to use all three of the people to do the lawn. Okay, so have a look at this. Maybe one hint is the fastest person could do the lawn in 3 hours, and he's getting help from 2 other people. So if you come up with an answer bigger than 3, it's wrong. It would have to be less than 3, because they're not interfering. They're working together, and so you would expect the answer to be somewhat less than 3. The other hint is it's not an exact number like 1.5 hours. It's a fraction, so you might want to estimate it in terms of hours and minutes once you find the fraction. Okay, so have a look at that, and we'll talk about the answer in the next lesson.